So what I'm going to talk to you about here is how you would approach the integration and that's the way that you test your hardware if you're going to like actually send it to space and you're not going with it. So you're not in a reduced gravity environment. It's actually going out there. And I think there are a lot of things here that actually do apply also to the reduced gravity environment. So I'll actually just point those out as I go. I just wanted to do a quick introduction and let you know. So a lot of my experience here that I'm going to be talking to you about comes from two missions in particular. We designed and built a student instrument that's on actually the OSIRIS-REx spacecraft. So if you are into asteroids and you have been actually following that, they're about to tag the asteroid and bring back some dirt. That'll happen October 20th, so 13 days from now. So my instrument has nothing to do with the tag. We were just looking at the X-rays that come off of the that basically come off the asteroid. Our operations were done at the end of last year, but we did manage to design and build and test that instrument that had to live for 2.5 years while it went on its journey to the asteroid in the environment of space, and then actually function once we got there. The second thing that I worked on was a spacecraft called it's called the Transiting Exo I guess Planet Survey spacecraft. So that's so that was built here at Tabley. This is George Ricker is the PI. And so that one, for tests, we were only going into basically Earth orbit. So we didn't have to travel quite as far, but we do have a number of cameras on that spacecraft that all have to work once we get up to orbit. And we're basically using it to look at stars and see when the light is dimming and basically identify the candidates of for Earth. So that one was a different type of test because the environment is very different, but we still had to make sure that those cameras were going to work once they got into space. And there's a whole bunch with that. But what I'm going to do here is give you a little overview of it, and then I'm going to skip around on this deck a lot. This is like a 90-minute lecture, and I'm not going to try to give that to you in 20 minutes because that wouldn't be fun for any of us. But I am going to highlight some of the key stuff here, and then I can also make this lecture available to you if you want to look at the slides. If you find this interesting later, I'm happy to share, and I'm also happy to answer any questions you have. But what I did want to start with, and I didn't start right here, is sort of what is different about the environment in space. So I don't know if anyone has but if you were going to make like a widget to do something on Earth, what is different about trying to make that same thing to do something in space? I'm going to witch out.
There might be environmental extremes like temperature.
Yep, and temperature. So temperature, what's different about temperature? Like, how many of you have ever had your laptop sitting on your lap? What happens?
It starts heating, but then there's a fan.
It's a fan, right? And fans can't really, so fans in space aren't as useful. So the fact that you're basically relying only on radiation and also conduction to move all of your heat away is very difficult. So that's great. That's the biggest one, I think. The second one is like another issue with space, and this is where I think it does actually apply to the back to the RGAs, is that say you build something on the ground and you put it into and it starts working and then it stops working, and then you can just go fix it, right? But if you have deployed your thing into space, unless you're going to go with it with your hammer and your wrench, you're probably not going to get to do much with it, again. So the need, I've worked on both the ground-based and space-based instruments, and the trade-off is definitely that you can make things way more complex if you're going to keep them on Earth, because you can get to them. And so when you're going in space, you want to make it as simple as possible to operate, as little as possible that could go wrong, and you want to test it a lot before it goes. And so the way I think that maps back to zero to doing hardware for for the parabolas is that, as Alvar, explained, and you get to see, you don't have a lot of, time. So you're going to get this parabola, and if your satellite or your hardware isn't ready to go and doesn't do exactly what you want it to do, you've now lost your opportunity. So if you need to change batteries because that wasn't done beforehand, or if something else happens, you've lost a chance to get your data. And as any scientist or engineer will tell you, data is important. You want to have as much of it as possible. So you really want to test before you get up there, before you get on the airplane, and make sure that everything's going to go smoothly. So this slide's not that interesting. So when it comes to spacecraft testing, you're going to do a lot. You're going to want to test it separate, levels. You want to test at the subsystem. You want to find your issues early at the subsystem before you integrate, and you have to take things apart to try to get into something. So you'll set up, this sort of idea from the beginning, from when you start getting your hardware to when it's all in one piece, how it's going to flow through. So the examples that I'm showing you here are from Rexus, but as you can see, we did a whole bunch, and it's a bunch of acronyms here, but we did a whole bunch of testing on the subsystems level, just the sensors and the electronics, and so here, this is the electronics
Becky, have you?
Type of sensors. Yep.
All we're seeing is slide number 1. Have you moved past that one?
Oh no. Okay. Yeah. You can't see the subsystem test example?
No, we're just still on.
All right,
slide
let me try
1.
again. I wonder if, all right. How about this?
Now I see subsystem testing. Yep.
Yeah, Zoom picks the wrong window, and anyway, okay, good. Okay, so this is where, like I said, there's a whole bunch of tests in here that talk about looking at different parts of the subsystems before you get everything, integrated. Then you're going to want to put things together and to think about how you do that. There is an order of operations that, depending on your system, actually matters a lot. So you don't want to integrate something that you then have to get at something else to test, or cover a bolt hole. And this sounds really obvious, but you'd be surprised at how often it happens, even when you have actually planned it out. So really thinking ahead and sort of going through the motions in your brain before you start them is super helpful. Then you're also putting this together. You're going to want to think about like the tools you need, all the torque, how you're going to fasten things, where you're going to do it, and any kind of GSE, which is actually the ground support equipment. And when you think of that, it's anything you need to test your hardware that isn't part of your hardware. And this is always forgotten. No one ever thinks about it, and it's a huge pain in the neck. And Ariel's laughing. I always get people coming to me. They're like, "I want to test this thing in your chamber," and I'm like, "Okay, but like, here's all the things we need to make that test happen." And so GSC is always a big deal, and it's always something that kind of gets left because everyone's excited about the test, but you need the jigs to hold things and the cables to make things happen, and sometimes you need to stimulate your hardware with something external, because in space you're going to get a star way out at infinity, and that's great. But when you're trying to test the test cameras, you might need to build a whole optical bench just to make it look like it's looking at a star out at infinity. So lots of things that may seem like, oh, I'll just do this test, and then you're like, oh, that's a thing. So really good to think about all the GSC you have to have. And this is just so one of my students made this for Rexus, and I loved his assembly in the flow, because he made it like that, like the subway map. And so each of those is like a piece of when things get put in. I don't think I put all of that in here, but it's a really nice example. Okay, then there are procedures, and it's super boring to lecture people about procedures, but unfortunately you really need them. And so you're going to start with a test. You're going to start with the document, which is like, here is like what I'm going to do. Here is the plan. It's going to talk about like your objectives, what you're going to measure. I can't tell you how many times I've had scientists say to me, oh, okay, well, in this part of the instrument test, we're just going to take some data. I'm like, no. I want to know what you're looking for and what is success. Like, what is success is huge, because you have to be able to move to the next step. The key to actually getting your hardware in space is being able to move to the next step. And it's really hard to move to the next step if you don't know what success actually looks like. So that is the plan, where you write that down. So that's all great. Once that's done, now you have to describe how you're going to do it. And that is the detail. That is the procedure. a checklist. So you have them because you want to save time. You want to think about what you're going to do before you do it. Make sure you have all the tools on hand, all the GSE, all the stuff I mentioned. You want to keep the hardware and the people in a situation where nothing gets hurt. So you review the procedure, you go to people who know what they're doing, and you get some input. Like measure twice, cut once, right? Once you've damaged something, you can be like months of schedule and time. And then of course you don't want anyone to get hurt. And then you want to have some documentation of what you did and how you did it. Because if you have a problem with that piece of hardware later, you're really going to wish you wrote down everything about what happened to that hardware before you got to that issue. Because one, it may help you, it may help you diagnose it. So you just want to write down everything. And usually when you get to this stage, everyone just wants to go, go, go. And they're like, oh, they keep making me write stuff down. But if you're testing hardware, please, please, please take time to write procedures and to write down what you did. You will definitely thank, in the future, you will thank you. Here's an example of the procedure that my students wrote for Rexus back in the engineering model days. And when I was pulling these out, looking for examples, I like how they left little Easter eggs for me. Like I was showing this as a nice example of how you want to say if there's an area that you're not supposed to touch because the material, like the paint on it, is sensitive. They did indeed indicate that, but also suggested that we assemble it with our minds. So it was, maybe that's not the best procedure writing, but it makes for a chuckle when you get to read it later. The other thing I wanted to point out in here was you want to be specific. What kind of tools do you need? What kind of screws? Not just give me some screws, but what size? Because you want to have those on hand when you're doing this work, especially if you're doing it in like a controlled environment, like in the clean room. You don't want to becoming in and out of a clean room, having to degown to get stuff. You want to have it all there, when you go in. So think like IKEA directions to like times like 100, right? With everything really written out for you. Oh, and this was a quote that I love, from Lincoln, which is like, we always have time to do things over, but we never have time to just get it right? No one wants to spend time up front writing procedures and thinking about the test, but everyone's happy, like, oh, we messed up now, we just have to fix it. And that's great, but a little bit of time up front. And, it's kind of like that saying where you always, if you lose something, it's always in the last place that you look, right? What goes wrong is always the thing that you didn't test or you didn't write down or you didn't think about. So there's always going to be something like that. But it's good if you can kind of minimize that list by thinking of the big things up front, right? Okay. So types of testing. So instrument testing and hardware testing before you get up there, and I would think this is true for any hardware that you guys are going to fly as well. The testing part is so much fun. I love INT, and part of it is like, when like you meet a new friend in that first couple of weeks, you just learn all the stuff about them. Is like so fun because it's all new. It's kind of like that. Like your instrument or your hardware is really going to talk to you and tell you exactly who they are and what they're like, and it's going to have a bunch of surprises that you didn't know. And this is when you really get to know your hardware, and that's important whether you're sending it up to a flight in an airplane and you're going to expect it to do something in the quick, short the time you have, or if you're sending it to space, never to see it again. Kind of where the friend analogy breaks down a little bit, but it's all good. So the kinds of tests you do are the functional ones, where you want to make sure that your hardware is working. It's a test that you want to repeat after you've done something to it. So if you're going to put it through environments, check for launch vibes, you want to check that it's working before and check that it's working afterwards. Kind of like when you do a study and you only change one variable at a time, so you can have a controlled study. Similarly here, you want to have a baseline. So when you subject it to the environment, you can go back and check the baseline again, and that's important to have. So a functional test will be kind of an easy test to run that checks all the major boxes that you can do over and over again. Then there are tests that are going to show that your thing's going to work. You're going to get the performance that you want. So on Rexus, these were harder because our CCDs had to operate at minus 60 degrees or actually colder. And because of the way that the instrument was built, the radiator had to have a view of deep space in order for the CCDs to reach that temperature. So we couldn't do that on the desktop. We couldn't sit in the lab and have the radiator looking at at room temperature Earth and turn on the computer and get the CCDs cold. So we had to put it in vacuum chambers where the walls are cold, and we can actually cool the e-box and make it look like it's seeing space. And that was really expensive, and it took a lot of time. So the performance tests you might not get to do as often. You want to be really careful with those and make sure that that you get what you're looking for. Then, if you're going to fly in space, you need to make sure that you're going to survive the ride. So that is your vibe test, right? You're not going to, once you get up there, it's going to be okay from a vibe perspective, but you have to get there. So the thermal, like we talked about earlier, you're going to experience a lot of, you might experience a lot of temperature. You might be going from cold to hot, especially if you're in low Earth orbit. And you want to also validate the models that you have that explain how your instrument is going to work in space. You want to know that you got that that is right, so you can use your model to predict the on-orbit behavior. And then you may also want to look at basically EMI, which is are you going to electrically interfere with, are parts of your spacecraft going to electrically interfere with other parts of it? And this is a bigger deal. This depends on what kind of data you're trying to take. One of the CubeSats I'm working on right now has a giant, RF payload. So EMI is a huge issue. If the spacecraft is, it is just broadcasting like EMI, then we're not going to get the data that we're looking for from the payload. All right, so this is what a vibe test would look like. Here is Rexus sitting on a cube that basically is going to shape. It's a little bit difficult when you've spent all this time carefully assembling your instrument and like making sure nothing happens to it, to then bolt it to a table and shake it. It doesn't feel good. But so it's not for the faint of heart, but you have to do it if you're going to survive the launch. And one of the tricky things is making sure that you don't overshake. You want to vibe it just enough to be sure you're going to survive launch, but not so much that you break something. And so what you're looking for is that the modes of the system, so the red here is before we did the vibe, before we tested it, have not changed between the pre-test and the post-test, so that when you get on the spacecraft, you get the launch vibe through, you don't shift anything, cause something to break. We actually had vibe tests that failed because one of our screws wasn't fastened actually right, and you can't really tell that just by looking at it. So we had to do an entire fastener redesign, and this the test that you're seeing here is after we did all that. So that was super fun. So for thermal design, you usually have to put it into a giant vacuum chamber. They're super fun tests. I really love watching the thermal behavior go exactly as predicted. It's super satisfying. The thing about thermal about this kind of testing is it takes a long time. Physics, you don't get to cheat anything here. You're just sitting there and you're waiting for for temperatures. So you generally will do like a number of cold and hot your cycles, usually around 8. And depending on the range that you're going to actually experience when you're in space, you want to go a little bit colder and a little bit hotter. And you're doing that to look for workmanship issues. Are the boards all soldered, all soldered together correctly? You want to stress it just enough to see if anything is going to kind of happen that you want to see happen on Earth, when you can still actually fix it, not when you go to space. Then during that hot and cold, you're going to spend some time at hot and some time at cold. And these are basic balances. And that's to allow things to get to the same temperature, to have the temperature stop changing, and check that the model you have actually matches the behavior of the instrument. And that's where you can start to update the parameters of the model to match what you really saw happen. So quick story, for tests, we had a number of cameras. There was 4 of them. We had a chamber for each camera. And we ran TVAC tests for a year. And there was a period of 6 months in which there was always a camera in one of the chambers. Sometimes there was one camera in all chambers. Sometimes there was just one camera in. And if there was a camera in a chamber, then the facility had to be staffed 24 hours a day. So we ran 7 days a week, your ops for this for 6 months. And tests, another quick thing is during the term, so during the TVAC, the testing, God, I could talk about tests, INT for like an hour, but I'll try not to. The way that the cameras are made for tests is that they're not actually in focus until they're cold, until they're at operating temp. So they're designed because it's going to contract when it cools down. So there's a piece in there that we had to design, put the camera into the TVAC chamber, get it down to minus 80, the 5, and say, oh, is it in focus? Oh, it's not. Okay, bring it back up to room temperature, take the camera out, take the shim out, adjust the shim, put the shim back in, put it back. I mean, and I came in as INT lead like late in this, and they had already decided like no, focus mechanism, and I was like, I feel like the INT lead didn't get a say in that whole no focus mechanism decision. So you're trading the reliability of a mechanism against a lot of work and integration and test. Because to give you an idea, to get that camera in the chamber, get us down to temperature, that was a week. That's a week right there. Then you find out you have a focus problem. It's another week to get back up to temperature, and then you're going to do the whole thing again. So the TVAC is super fun, super boring, and can be kind of a thing. Okay, I am running out of time. So all I wanted to say, systems engineering and INT can be overwhelming. All the problems happen. It's also the most fun. There's never a dull moment. You need to think carefully. You have to keep this big picture without getting too caught up in logistics, but you have to also take care of logistics. So it really works all parts of the brain, which is super fun about it. Just the traffic control. So you're constantly changing the plan. You've got one plan. What is the quote? No, I guess plan actually survives the first contact, right? That's totally true in INT. So I just told you, spend all this time making these plans, and then you're going to get in there and you're going to be like, ugh. So you're still going to be really, really happy you spent time, making, that you have some idea what you're doing, but you're going to have to be ready to make changes as you go. And that's what makes it so fun, and interesting, I think, to do. Blah, blah. Man, my thing is kind of slow. Oh, I love this comic. So they're asking, if Wally had finished up for the day, his projects, and he says, no, I took a calculated risk that others would not, be done. So me being late would be irrelevant. And the best part about this is it's what I call sort of space chicken. Everyone is trying to not be the second. You want to be second slowest to the bear. So here's the bear, which is schedule, and you want to be second slowest so someone else gets in trouble for being late and not you. And that's pretty much the whole way that INT goes on anything. So this is having a baseline schedule, executing, being ready to restructure. This is a picture of 2015. Here we got so much snow. This is the dorm over on Vassar Street, and this is how high the pile of snow was. And this was right when Rexus was getting all of the parts for, to integrate. So we couldn't get any parts here. The T wasn't actually running. Everything was delayed, and you just have to be ready to restructure, because you can't stop snow. Not in the plan, even if you have tried. All right. That's it. I have some real life examples, but I'm totally over time, so I'm going to stop now. I hope this has given you some idea of testing in space and what might come next after your RGA.